That moment you feel a little warm, reach for the thermometer, and wonder, how does this tiny glass tube know your temperature? It's one of those everyday objects we barely think about, yet its ability to gauge the invisible force of heat is surprisingly profound. From a fevered brow to checking the oven, the humble thermometer performs a quiet magic. But what's really happening inside that slim glass column, giving us such a precise reading? The story begins not with magic, but with a fundamental principle: thermal expansion. Think back to early scientists like Galileo Galilei, who, around the turn of the 17th century, created one of the first thermoscopes, essentially an air thermometer. He observed that substances change volume when heated or cooled. It was a crucial insight, laying the groundwork for the more refined liquid and glass devices we know today. At its heart, a simple thermometer relies on a liquid, often colored alcohol or mercury, encased in a sealed glass tube. When this liquid warms up, it expands, and when it cools down, it contracts. This movement is what we see as the rising or falling column. But why does this expansion happen at a molecular level? It all comes down to kinetic energy. Heat is essentially the vibration and movement of atoms and molecules. When you introduce more heat, these tiny particles gain more energy. They start moving faster and more vigorously. This increased jostling forces them to take up more space, pushing against each other and causing the overall volume of the liquid to expand. The clever design of a thermometer maximizes this effect. The liquid is contained in a bulb at the bottom, which has a larger volume. This bulb is connected to an extremely narrow, almost hair-thin, capillary tube. Even a tiny expansion in the bulb's liquid volume causes a significant, visible rise in the column within that tiny tube, making minute temperature changes easy to read. To ensure accuracy, the space above the liquid column in the capillary is often a vacuum or filled with an inert gas like nitrogen. This prevents any air pressure from interfering with the liquid's expansion, and for mercury thermometers, it also stops the mercury from boiling at higher temperatures, maintaining the integrity of the measurement. Finally, calibration gives us those familiar numbers. Scientists like Daniel Gabriel Fahrenheit precisely mark their thermometers using fixed, reproducible points, like the freezing and boiling points of water. These points became the universal benchmarks, allowing us to compare temperatures anywhere in the world with consistent results. So, the next time you glance at a thermometer, remember it's not just a glass tube and some colored liquid. It's a beautifully engineered dance between heat and matter, a testament to human ingenuity translating the invisible world of molecular motion into a number we can all understand. Simple, yet profoundly insightful. What other invisible forces do you want to explore next?